This is exactly what I'm going to do, actually. This is, so the suggestion is, what if I zoom in or zoom out on the figure? There's a very clever trick here. We know how one-dimensional and two-dimensional objects or measurements act when we scale them up and down. So for example, if I take some weird little curvy shape like that, and I let's say I have it on a piece of paper and I bring it, you know, half as close to my face, so twice as close to my face, twice as close, and it's a unit of length. You could ask, well, how long does the second figure compare to the first figure? It turns out because length is a one-dimensional measurement, it's always the same thing. It's always, this one is twice as long. And that, it turns out, is true for every one-dimensional measurement, one-dimensional object. That if you scale it up by 2, the length doubles. On the other hand, if we take a two-dimensional object, like a square, and we bring that closer, we scale that up by 2, the area of that quadruples, right? There's my picture. You can see there's clearly 4 squares the same size. So, and it turns out if you do this with a circle or with any weird two-dimensional shape, this always is true. This is somehow a real indicator of what dimension you're at. If you scale it up by 2 and it doubles, the size doubles, it's one-dimensional. If you scale it up by 2 and the size quadruples, it's two-dimensional. So we can just check Sierpinski's triangle and see what it does. So this is great. So, okay, now we have a strategy. We're going to scale it up by a factor of 2, and if the space it takes up doubles, it is one-dimensional. If the space it takes up is quadruples, we know it's two-dimensional. Everyone good? So we'll do this. We scale it up by 2. What happens? Well, I can see what happens here. I've got one of these here. I've got 3 of them there. And they're exactly the same. It's triple. Now this wasn't in our plan. This is something really wrong here. What's going on? Well, apparently our different way of doing this has forced us to an answer to this question that we didn't expect. Either one-dimensional or two-dimensional. It's neither. In order to have our old conventions and understandings of dimensions still make sense, this can be neither one nor two-dimensional. It's got to be something else. And in fact, it is possible to figure out exactly what dimension it has to be in order for it to triple when you scale it up by 2. It ends up being the log base 2 of 3, which is about 1.5849 dimensions. This is one, I think for me, when I saw this, there was a sense of like my whole brain exploding. And we're not even done yet, because this just came from 2 relatively similar ways to build Sierpinski's triangle. I'm going to take questions at the end for this one. So there's so much more going on than we thought, and we see this not on our first time building it, but on our second time building it. How much deeper does this go? How much more is this showing us is really happening underneath the surface? Well, I'm going to show you the third method, which also made my head explode when I saw it, which is using Pascal's triangle. Yeah, this is crazy. Pascal's triangle, many of you have seen this. It has this very nice property that this is one drawn with hexagons, but you can draw it with squares or circles or whatever. But every entry is the sum of the 2 entries above it. So for example, if I look at the 56, for example, or one of the 56s there, that's 21 plus 35. The 2 entries above it add up to the one below it. And you can check that every entry has that property, and that's how we build it from the top down. So it's triangle, right? I mean, aside from that, there's no reason to really hope that it'd be connected to Sierpinski's triangle, except one day, someone got bored and started coloring them in and said, well, what if I color the evens one color and the odds another color? So there's the odds, purple, and the evens white. And then they zoomed out, and let's sort of highlight the colors for contrast. I'll go black for the evens and red for the odds. So this is not This is only Pascal's triangle with the evens and odds colored in differently than I'm going to show you in this next picture. That's where this comes from. That's what it looks like zoomed out. What's going on here? This third method is even more mysterious than the last one in a way, because what it suggests, what it says to me is somehow there is some kind of connection between numbers and fractals. Which, I mean, I don't know, and maybe I'm just being sort of overly simplistic and saying maybe there's just some really simple way to explain this and there's no deeper connection. But to me, it seems that this is telling us that something more is going on. In fact, there was some really big news on this topic about a week ago, which is that the question of partitions was just solved. Partition is a way to break a number up into a sum of smaller numbers. So for example, if I want the partitions of 5, I could write it as 5, 4 plus 1, 3 plus 2, which we're not going to worry about order, so that's the same as 2 plus 3. 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and all ones. And that's all the ways to do it. And you can check that out on your own, like see if you can break it into whole positive numbers any other way. So there's 7 partitions of 5. And this seems like a problem you might get on a MathCounts exam, right? Like how many partitions are there? Find a general formula. People were looking around for a general formula. From hundreds of years ago, I think people started asking this question. And it's really hard. No one could find a general formula. So about 100 years ago, some of the greatest mathematical minds found a good way to approximate how many partitions there are for big numbers, like 200, not even that big. Really hard. Progress has been made, and last week, a researcher named Ken Ono at Emory University just cracked it and found a closed formula. So this is happening right now. And what was his insight? Well, in a newspaper interview, he said, the insight was that the numbers somehow have a fractal structure. And this is his quote: "We prove that partition numbers are fractal for every prime." So maybe I am being overly simplistic to say that the fact that we can build Sierpinski's triangle from Pascal's triangle in this way means there's some deep analogy between natural numbers and fractals, and yet people are using that very idea on the cutting edge of mathematics today to prove things that have been resistant to proof forever. A challenge for you all, if you want to, is to calculate the partitions of every number between 1 and 10. And you'll see how tricky that gets as we go. I have one more method to show you, and then I'll take